Alright, so methods of proof. We already saw vacuous before. And we already saw trivial proofs. So those two are pretty much the easier two types that we see. And actually, we don't even really see them that much. But they're important to know because they're based off of the truth table for if P then Q. And we have one more that's going to be based off of that truth table. So before we start that, we're just going to write that down. So we have if P then Q. And we want to know exactly when it's going to be a true statement. So we'll have every possible combination of P and Q being true and false. And remember that if P then Q is only false when the antecedent is true, the consequent is false, which is right there. And there's the rest. We want to look at a direct proof, which is going to focus on this case right here. So for a direct proof, we're going to assume that P is true, and then we show that Q follows from that truth of P. And this is sometimes a lot harder than the previous two that we saw, but it's more useful, and it's going to get us to be able to prove normal mathematical statements. And so we focus a lot on the integers. Which are partitioned by both even and odd integers, remember. So if we have an even integer, we know that we can write any even integer, a general even integer, as 2 times k, where k is also an integer. And any odd integer as 2 times k plus 1, where k is also an integer. And you can see that's right, because if we add something like 2 or 10 or 20, these are always going to be 2 times something. 2 times 1, 2 times 5, 2 times 10. And similarly, if we look at 2k plus 1, if I have 3 or 11 or 17, this right here would be 2 times 1 plus 1, 2 times 5 plus 1, 2 times 8 plus 1. So any even can be given by 2k, any odd can be given by 2k plus 1. And that's just for integers. Only integers can be even and odd. But those are the ones that we look at the most. And if we're given a statement, we want to make sure that that variable that we're given, like n, actually is going to be in the integers. Because if they say let n be a real number, and we prove a case for integers, we're wrong. Alright, so let's say our claim is let n be an integer. If n is even, then n squared is even. So before we actually start the proof, we want to make sure that it's actually true, and it seems like it is, right? If we have 2, its square is 4. If we have 10, its square is 100. If we have 8, its square is 64. But we can't prove it like that. We can't just list out a bunch of cases where it's true and say that it's true. We have to prove it for every single possible case. And if we don't check every single case, then we can't say it's true. But like I said, we can't check every case. So what do? We have to do a general case. And if we do a general case, then we can cover every single integer, every even integer at once. And so usually we want to do a proof sketch, which will kind of guide us through what we're going to do in the proof, and then we'll do the actual proof. But here, it's a pretty simple proof. All right, so we're going to let n be an integer. We just want to repeat that. And then we're going to assume P is true and show that Q follows. That's a direct proof. So assume P. So assume N is even. And for this, well, for us, that means that N can be written as 2 times K for some integer K. So there's us assuming that P is true, and then we have to show that Q follows from that. So if we look at N squared, that's going to be 2K squared, which is 4K squared. So now we want to know, can we actually write that as 2 times an integer? And it turns out that we can. This is really 2 times 2K squared. This thing right here is an integer. And there's actually a name for that we want to talk about, because to a lot of people 2K squared might not seem like it's an integer, or if you just want to ask in general why, how do we know that's an integer and not some rational number? And we're going to show that in a minute. But here we're just going to call this 2L, where L is that integer 2K squared, just for simplicity. And so we squared N, and then we got an even integer. So we can say, therefore, if N is even, then N squared is even. And then we'll put our tombstone right here. That was made by P.R. Halmos. We used to write QED, but he liked the tombstone better. If you want to look him up and see why he did that. Alright, closure of the integers. So if we take an integer, let's say 3, and we divide it by another integer, 7, we want to know, are we going to get another integer? It turns out no, not in this case, right? This is not inside of Z. And what that tells us is that the integers, Z, are not closed under division. But if we multiply two integers, let's say 3 times 4, 5 times 12, any two integers that we multiply, we're going to get another integer. And that's because they're closed under multiplication. And similarly, if we add or subtract, subtraction is included in addition. If we add two integers, then the same thing is going to happen. We're going to get a third integer, and that's because they're closed under addition. And again, that includes subtraction. So if we have any combination of these two operations, we're also going to get another integer. So that's why we can say confidently that 2k squared, that's just 2 times k, is also an integer. It's when we start dividing that we get into trouble. So I can't say 2k squared minus 1 over 3 is an integer. That may not be true. But if I just have 2 times k plus 1 times 41 minus 6, that's definitely going to be an integer. And closure is how we basically prove these. If we didn't have that, we would be in some trouble. So let's look at another example. And we're going to say that our claim is let x be an integer if x is odd, then 3x plus 7 is even. And to prove that, we're going to do the same thing. We're doing this by direct proof. And so we would assume that x is odd. And that tells us that x can be written as 2 times an integer plus 1. Now I usually use k, it doesn't matter. We could use anything, so we could even say 2p plus 1, where p is some integer. So now if we've assumed that p is true, our statement p, maybe it wasn't a good idea to use p for the integer, our statement p. So if we look at 3x plus 7, we know that's really 3 times 2p plus 1 plus 7. And so that's going to be 6p plus 3 plus 10. I'm sorry, plus 7, which is 6p plus 10. Now we want to know, can we write that as 2 times an integer like it's supposed to be written? And it turns out that we can. This is 2 times 3p plus 5. And by closure, 3p plus 5 is also an integer. So this thing, we could call it n if we wanted to. We don't have another n being used right now. So this is 2 times an integer, n. And that means that it's even. And so we've completed the proof. We showed that if x is odd, that 3x plus 7 is even. Try to get this. There we go. And so we'll put our tombstone and we're done. Right? Let n be an integer. If 5x minus 7 is even, then x is odd. And so, in this case, you can see what's about to happen as soon as we start. If we assume that 5x minus 7 is even, then now we have 5x minus 7 is equal to 2k. And the goal is to show that x is odd in this case, so we would actually have to get x by itself. We'd have to add 7 divided by 5. It turns into a big mess. We actually can't do it this way. But what we could do is use the contrapositive. Remember, the contrapositive is logically equivalent to the conditional statement. And it says if not Q, then not P. So if we rewrite our original statement, if x is even, then 5x minus 7 is odd. It virtually becomes the last problem that we just did. And I'll let you complete that proof, but as soon as we prove this statement right here, and this is true, that implies that this statement right here is also true. So we can use a direct proof on the contrapositive if we can't do a normal direct proof.